Okay. Good afternoon, everyone. Let's get started. Only 4 of us, 5 of us. Okay. I know it's near end of the semester. We only have in addition to this class, we'll have 3 lectures. This Tuesday, Thursday, and next Tuesday, and then we're done, right? But I think the final items I just want to mention, last homework assignment released today. We still got 2 weeks to finish, but don't worry, the workload is not large. Maybe 3 problems asking you to implement some Hamiltonian multi-color sampling, I guess, and on some toy problem, but just make sure to hand in or submit in Canvas on time, because when we near the end of the semester, the office of the registrar has hard demand that you must submit your grades by time. That means if you request for extension, that will be much more harder. Okay, so let us continue with Bayesian neural networks. So in the last lecture, we talked about a very classical, very popular Bayesian inference method. It's called Bayes by backpropagation. So it's a relatively straightforward application of variational inference, right? So variational inference, I know that if we want to estimate, want to compute the true posterior distribution of the random variables given the data, it's so hard. We don't know the form, right? So then the compromise is that, okay, I'm gonna assume some approximation family, right? Easy approximation family. Then my problem is that I want to find out a best one in this approximation family, which is closest to the true posterior distribution, right? This is a variational inference framework. And that means first, we're gonna specify the approximation family, right? For example, you can assume your approximation posterior is of a Gaussian form or of a fully factorized form, that's called mean field family, right? Or whatever other form. And we need to specify the approximation family. And secondly, you want to construct a variational evidence lower bound, right? So the evidence lower bound can be written as an expectation under the approximate posterior of the log fraction of the drawn distribution over the approximate distribution, right? So why we can simply maximize this guy, because this evidence lower bound plus the KL divergence is true posterior. Sorry. KL divergence from the approximate posterior to the true posterior, right? Their summation will be the model evidence, right? So since model evidence is fixed, so we maximize this guy, it is implicitly minimizing KL divergence, right? And just directly or explicitly minimizing KL divergence won't be possible because you don't know what exact form of the posterior, right? But computation of this log fraction of the drawn probability over the approximate posterior is usually much easier. So then we kind of apply this framework to inference of Bayesian neural network, right? So our idea of this Bayes by backpropagation is that, okay, first, in the first step, we're gonna assume my posterior distribution of the neural network weights can be represented as a fully factorized Gaussian, right? So here which means I'm gonna go over every element in the neural network parameters, right? And I'm assuming, okay, they're fully factorized or independent Gaussian and parameterized by the mean and some free parameters of rho I, right? But this rho I is free, meaning it can be arbitrary value, real value. But when I add one, sorry, it's not a logarithm. It's an exponential, sorry. It's logarithm 1 plus exponential rho I, right? you're doing such kind of transformation, you ensure that, okay, your variance parameter of your approximate posterior is always positive, right? You cannot use a negative variance. Right? So yeah, that's first step. We simply assume the posterior is approximated as a fully factorized Gaussian. And secondly, we just construct a variation evidence lower bound. This is just very, very standard. We just take expectation over Q of theta, and you take logarithm. You have typically a Gaussian prior over the neural network parameters, and then you got n samples, right? And for each sample, suppose you're doing regression, so you're using Gaussian likelihood. So you got your neural network output as your prediction, right? And you got some variance parameter, likelihood variance parameter or inverse variance parameter. So this is a joint distribution, and then you divide it by your approximate posterior distribution, right? And then you then your goal is just to maximize this evidence lower bound, right? But here there's two problems, right? First, when you do the expectation, let's go back here. Right? And here our notes before. When you do the expansion of this expectation, you found out, okay, in addition to those analytical form, there is one term, no, it's actually a type of terms, which is the expectation of the log theta likelihood under the approximate posterior of the model parameters are analytically intractable. This is reasonable because those W or the theta I wrote a minute ago, they are coupled in a very highly nonlinear way inside neural network to generate the final output, right? So it's impossible for you to directly compute this expectation. Even you're taking expectation with some kind of Gaussian distribution is very friendly, but the function which couple W are highly nonlinear to W. So meaning the likelihood here. So you're not able to compute the exact expectation. So how can we address this problem? Any idea? Any thoughts? We spent, yeah, David. Yes, we use the so-called reparameterization trigger. This is really important because I mean, in the future, if you want to do some like Bayesian stuff for neural networks, this reparameterization trick is kind of a standard tool. Right? So the idea is that, okay, I'm gonna first parameterize this W because we're assuming this QW, right? The posterior approximation is Gaussian. That means we can reparameterize W as a function of the mean of this Gaussian and multiply plus some standard deviation multiplying with some random some standard Gaussian noise, right? So in this way, if I take expectation under Q of W, it is equivalent to take expectation under the distribution of the Gaussian random noise. And then you can take the gradient inside this, when you take the gradient of the expectation, you can safely move your gradient inside expectation because the distribution for which you take expectation is constant to the parameters want to take the gradient. So you can just move in, right? Otherwise, we discussed before, right? If you just move your gradient inside here, like under the original posterior, that won't work, right? That is wrong. Right? That's because your variational posterior also contains parameters, so you want to take the gradient. So it is not valid. And doing so can allow us to very conveniently and easily get stochastic gradient, right? Every time you just sample a Gaussian noise, instance Gaussian noise, then you plug in the log likelihood of every data point, and then you take the gradient with respect to the parameters of your variation posterior, and that's it, right? And then we can combine the mini batch trick we discussed before, right? So remember, the mini batch trick essentially is another application of the stochastic optimization where you partition the big data set into many small mini batches, right? Every time you random pick out one mini batch, and then you compute the gradient just of the log likelihood just within that mini batch, and then you amplify it by multiplying this factor to ensure your stochastic gradient is unbiased, right? I'm just quickly refreshing our mind. Right? If you feel like strange or feel uncomfortable about all of this, please spend some time to reviewing our slides we discussed before, right? But if you feel like okay, this all sounds natural and it's reasonable, super comfortable, that's very good. Okay, and then we can conduct stochastic training or stochastic variation inference, right? So we initialize our variational parameters for the approximate posterior randomly. Then we'll go through I'll go through a number of updates T, right? Every time we sample a standard Gaussian noise, right? And then we represent our neural network parameters with the Gaussian noise and also the variational posterior mean and the standard deviation, right? Yes, here the representation of the weights, reparameterization of the neural network weights in terms of the random noise and the neural network and the variational posterior parameters, right? And then you can calculate the gradient of the log likelihood within each mini batch. You can get your stochastic gradient. Then you just apply stochastic gradient ascent, right? Because you're maximizing the evidence lower bound, right? And you also need to ensure that your step size or learning rate satisfies some criterion, right? To ensure eventually you're going to converge to some local minimum or local optimum. Okay, any question regarding the base back by back propagation? Okay, great. So then we show some performance reporting in the original paper. First compared with the non-Bayesian learning of the Bayesian neural network seems comparable to the best approach, right? And if you look at the typical learning behaviors, we found that actually using stochastic variational inference training or learning of the variational posterior seems to tend to explore even better surface of your objective function and return better test data. Okay, to summarize, based by backpropagation, it's kind of a state of art neural network posterior inference is very popular. Very simple and very popular. It achieves the same scalability of the stochastic gradient descent, but it can estimate posterior distributions. That's very useful, right? And the core idea is variational inference plus the reparameterization trick. So, and the reparameterization trick combined with the stochastic optimization serves the foundation of nearly all the modern Bayesian neural network training. So this is very important. Okay, next we're going to talk about the two popular Bayesian neural network models. One is called auto-encoding variational base. The other is called general adversary networks. I guess all of you have heard these two types of networks before. Is there anyone who never heard of them? Okay, that's good. Yeah, first one, autoencoder variational inference, right? Variational base. So first, what is autoencoder? So this kind of neural network, perhaps it's more people who are doing like image processing are very familiar with autoencoders. So the idea is to find out some compressed or low dimensional representation of some high dimensional data, typically images. So you got an image, typically can be very large according to the resolution. you got 1024 by 1024 image, you can consider like 1 million pixels. It's very large, right? So it is inconvenient to store to transport them through networks. So a natural motivation will be, okay, can we compress this image, right? We just extract, we just reduce the redundant information, just preserve the key information. And then at some other places, for example, when it is sent to some other desktop or laptop or app, right? You can just use some decompression technique, right, to recover the image. So that's what autoencoder is trying to do. Right? We want to use neural network to compress a large image or any other high-dimensional data into a low-dimensional representation, and we want to use another neural network to recover the original image or high-dimensional data. So the neural network who does compression is called encoder. So this borrows the ideas of the coding theory, right? They call it encoder. They try to encode the high-dimensional data into a compressed representation. Right? People call this compressed representation as code. And then the neural network which decompress the code or recover the original high-dimensional data is called decoder. Okay. And so you can imagine autoencoder is kind of like two steps. First, I'm going to apply the encoder network to get a low-dimensional representation, namely code, of the original high-dimensional data. Then apply decoder network to reconstruct the original data. So dimension reduction is a very important practice, not only for saving the space, but sometimes it's also help denoise, right? Because the data, when it stands in high dimensional, you can imagine that there are a lot of like redundant information, right? For example, if the sky, you know that all the sky, most of the pixels are just blue. It's not necessary to store like 10,000 blue pixels, right? You may just store 1 or 2 of them, right? And there also can contain a lot of noises like here, right? So through the compression procedure, we hope that we not only extract the unique and useful information, but also we can reduce noise. Okay? So that in the decoder step, right, when we run the decoder network, we can not only recover the effective information of the original image, we can also remove the noises. So this is like two common advantages of using autoencoders. One is to get lower representations, right? And the other is try to denoise. So how does the traditional autoencoder models work, right? So as we mentioned, right? So we gonna design an encoder network and a decoder network, and then we're gonna collect a bunch of examples, right? For example, I can collect 1,000 images or 1,000 pieces of audios, right? Whatever high-dimensional data you have in your hand, and then I'm gonna construct a loss. This is called reconstruction loss. For every example in my data, right, I'm gonna first apply my encoder network to get the code, the low-dimensional code, right? And then I apply my decoder network to the code to reconstruct the original data. I want to minimize the difference between the original data and my reconstructed data. And then I minimize this square reconstruction loss to estimate the parameters for both encoder network and decoder network. That's how the standard or traditional autoencoder models are trained, are learned, and determined. Any questions so far? So you can see this is a typical unsupervised learning model, right? You just collect a bunch of high dimension data. You don't need to do any supervision. You don't need to do any labeling, all kind of stuff. Right? This is why autoencoder is the typical unsupervised learning approach. Right? So now let us transit from the traditional autoencoder to a probabilistic autoencoder. How can we perform this learning of encoder networks and decoder networks in a probabilistic scenario? Right. So we call this probabilistic autoencoder as variational autoencoder. So first, we're gonna view the code, the low dimensional representation as some random variable, latent random variable. Okay. So that means using our variational autoencoder, we not only give you the compressed representation, but also give you some uncertainty about my compression. Right. So we will code as the latent random variable. So we want to estimate the posterior distribution of the code H given the high dimensional data. And in general, we're not assuming the parameters in the two networks are random variables as well. We're just assuming they are hyperparameters. We just need point estimation. That's how the original variational autoencoder model is developed. But of course, you can extend it. We can extend the standard model and to allow us to estimate posterior distribution for the neural network widths as well. But here we just to stick to the to introduce this type of method, we just stick to the original model definition. We assume the neural network weights are just fixed, not fixed. It's some hyperparameters which we only need point estimation. Okay, so since this is a probabilistic model, right, we should define some probabilistic model. So we're gonna define a distribution over this decoding procedure. So we will this decoding procedure as a probabilistic generative procedure. How we define it. Right? So first, I'm gonna sample my code for every example n from some part, right? And then, given my code, I'm gonna sample the high dimensional data axon through this decoder network. This is called probabilistic decoder. You can see this is a very simple Bayesian model, right? You got a prior over H, right? A code, and then given H, you sample the actual high dimensional data axon. And typically, we're assigning a standard Gaussian prior over the code H. And according to the type of the actual data, actual high dimensional data, we might use different likelihood. For example, if your axon is a continuous value, then you might use a Gaussian likelihood, right? If your axon is binary, you might use a Bernoulli likelihood. So this is the modeling part. You can see that we only define a probabilistic model on the decoding part. This is called probabilistic decoding. Right? And then where does the encoder part? Where is the encoder part? How could we introduce the encoder? So, as we mentioned, right? Given this probabilistic decoder, right? So here, right, our goal is to estimate the posterior distribution of the code given actual high dimensional data, right? That's our goal. And of course, because HN has already been gone through a decoder network, so when you compute this posterior distribution, it won't be tractable. Right? It will be very hard. So we need some kind of approximation. So again, we're going to use the variational inference framework. And the encoder is defined as the variational posterior distribution of HN. In other words, we're going to use encoder to construct or define our variational posterior approximation. How can we do that? So in our previous examples, when we talk about Q of HN, typically we assume, okay, this could be Gaussian, right? For example, it could be some Gaussian and is parameterized by some mean and covariance, right? And want to estimate mean and covariance. And then in the variational autoencoder, it just changes the definition of the parameters of the variational posterior. So now we're not just estimating some value of mu n and Vn, the variational posterior parameter. Instead, we parameterize mu n and Vn, for example, as the neural network output of the encoder network. So you can view it mu n as the neural network output where the input is xn. And similar is Vn. That's how they inject the encoder network. So previously, we were assuming, okay, this is just some point, right? Specific to this example. And we might want to estimate this time to be 0.5, 0.1, whatever. This could be like 0.05, something like that, right? But now, I'm not gonna assume this is some kind of unknown value. I'm assuming this is an output of a neural network. It outputs some encoder network, and the input to this encoder network is xn itself. And I use this construction of my variational posterior approximation to conduct variational inference. That's called variational autoencoder. So we use neural network output to parameterize the variational posterior, namely the encoder. Any questions so far before proceed to concrete examples? Okay, great. So now, if we write down the variational evidence lower bound, it has the following form, right? So it is go over every training example. So inside this summation, it is the integral or expectation under the variational posterior. However, because this variational posterior is determined by the encoder's network's output, so we can view it as a condition on xn. Right? And the log fraction is the log joint probability. This is a probabilistic, the joint probability of the probabilistic decoder, right? And the denominator is the variational posterior, right? So this one again is determined by xn. Why? Because it is parameterized by the encoder's network, and input is xn, and output will determine the parameters of this variational posterior distribution, right? And of course, both the variational posterior and the probabilistic decoder distribution, when we calculate the expectation, it won't be easy to compute, right? It won't be analytical. Right? So we have to leverage the reparameterization trick plus stochastic optimization. Right? And in addition, if the data set is very large, you can also apply the mini batch stochastic optimization trick. Any questions so far? Okay, so now let us look at some concrete example. Right? First, let us assume, okay, your original data are continuous. For example, a colored image, right? So the image values, the pixel values can be normalized between 0 and 1, so they can be viewed as continuous. Right? So I want to find out, for example, this image of this force, right? A very low dimensional representation code, right? So first, we're gonna assign some prior over my code, which is a standard Gaussian distribution, right? And then I got my decoder network, right? The decoder network uses the code, the low dimensional representation as input, and then it can generate two outputs. One is for mean of your prediction. The other is for the variance of your prediction. And remember, this is actually the your reconstruction of your image. So this one, so both mu n and rho n can be high dimensional. Because they try to, the output of the decoder network try to reconstruct the original high dimensional data. Like take this horse image as example. You can imagine the prediction, the mean of the prediction is high dimensional, and also the variance parameter for the prediction is high dimensional as well. Okay. So you can view that, okay, through a bunch of like neural network layers, right? In the last layer, you're gonna generate two types of outputs, mu and rho n. Right? And then these two outputs are used to sample xn. So if we write down the likelihood of xn given your code hn, we can use Gaussian likelihood, where the mean is mu n, where the variance is rho n take exponential and take diagonals on diagonal. Right? So here again, we take exponential, it's just to ensure that your variance is positive. Right? And the diagonal is just for convenience. We're assuming that given your prediction, your output variance are independent to each other rather than correlated. Right? If they are correlated, then there are too many outputs you need to compute. Okay. If the original, the actual high dimension data is not continuous, right? For example, it's just binary, like this force, right? It's just this force image consists of like black pixels and white pixels. Okay. And how do we construct our decoder network decoder likelihood? Okay. We can use Bernoulli like. Again, the input to this decoder network is hn. The output only has one type of output, right? And this one type of output is further through some transformation, say sigma function, to transform it into the probability. Right? Then I use that probability to sample the binary observation in every element of this horse image, right? Binary horse image. So in this case, you can see that okay, the output of our decoder network is this one type of output, and then we can write down the likelihood. Any questions so far about these two examples of the decoder model? Everyone is comfortable? Okay, great. So then let us look at the encoder, right? Although there are like many choices of designing your encoder, but the most commonly used one is called Gaussian encoder. Right? So Gaussian encoder means that you're gonna use some Gaussian distribution to construct your variational posterior, right? How can we do that? As we mentioned that, we're gonna use the encoder network's output to parameterize my posterior distribution, right? Approximate posterior distribution. So given the input as the original high dimension data axon, right? Through a series of layers of neural network, right? At the final layer or last layer, we'll generate two types of outputs, Mn and eta n, which represents or correspond to the posterior mean and posterior variance. Then our variational posterior, which are parameterized by the encoder network, is defined as a Gaussian distribution. Of course, it's a factorized Gaussian distribution, right? And the mean is Mn, and the variance is the exponential of the eta n and take diagonal. Right? So this means that okay, I'm gonna construct a fully factorized Gaussian distribution to approximate my posterior, and then the mean and the variance of this fully factorized Gaussian are generated by the encoder network. Right? And then I got my Gaussian encoder, the variational distribution. I got my my decoder, probabilistic decoder distribution, right? Then I can construct a variational evidence lower bound, and then I use reparameterization trick and mini batch, stochastic mini batch optimization to estimate parameters for encoder networks and decoder networks jointly. Any question? It's a fairly straightforward applications of the. You can see the techniques is the same as Bayes by backpropagation. The only difference is how you design your variational posterior, right? And this paper, if you can look at the original paper, is called Autoencoding Variational Bayes. I think the citation is over 100K, perhaps 200K. You can take a look at that. It's very, very simple idea, but it appears it showed up at right time and increases a huge amount of attention. Okay, to summarize, variational autoencoder is to convert autoencoder estimation into a probabilistic inference problem. Right? So it just defines a probabilistic model for the decoder part, and the encoder is injected in your construction of the variational posterior approximation. Then you use the variational inference framework to estimate the parameters for both encoders and decoder networks. Right? It's kind of like state of art, but here is a little bit inaccurate. I would say some scenarios still state of art, but right now it is being replaced by more advanced approaches like diffusion generation frameworks. Those kind of stuff, right? But it's still very, very popular in image processing domain. Okay, any questions so far? Everyone feels good? Okay. Okay. Next, let us talk about this so-called generative adversarial networks. Right? So, if you look at this paper, the original paper, the first paper about this general adversarial networks, also known as GAN, was published in 2014 in NIPS, and then it kind of like becomes extremely hot, and then like in just a few years, like there are hundreds of variants of this GAN version. So people like are kidding that okay, we have opened a zoo of GANs. So what is GANs, right? The goal of GAN is to construct or generate images which respect certain distribution. So let us start with a classical problem, right? To illustrate the scope, right? Consider we have a uniform random variable x, right? Say x comes from 0 to 1. You just sample it from a uniform distribution. Can we conduct some kind of transformation or mapping T such that after transformation, so you know T of x will also be a random variable. So we want to know that if we can make T of x to respect some certain distribution. Okay. I guess many of you have heard this kind of problem, right? If I got a uniform random variable, right? What kind of transformation can make the transform random variable obeys some given distribution? The answer is you're gonna take T, the transformation, as the inverse of the cumulative density function of the target distribution. It's not hard to show that. I'm not going to show this one. It's pretty easy to show this. I'm just telling the conclusion. It's in almost every introductory statistical book. But here it tells us one thing, right? First, in practice, in practical work, we always some kind of need to generate images of certain distributions. For example, I want to create an image of cat. Right? Of course, not to just copy some existing cat image. I want to create a new cat image. Or I want to create an image of some animation character, like automatically. And how can we do that? And in such kind of cases, you even do not know the distribution, the density form of your target distribution. Right? You only know a bunch of instances. For example, if you want to create a cat image, right? You might just collect a bunch of cats. I mean, there are images, and you know, okay, on the line there must be some distribution, but you don't know what's the form of distribution. You want to use those instances from your target distribution to learn some transformation, so that you just transform some uniform random variable. It can give you another instance of the cats. Right? That's our goal. Right? That's actually very useful in advertisements, in game development, right? In the game, electronic game development, people always want to create some new character, right? They don't want always pay like $10,000. I mean, I just randomly say something, right? To have some like painter or some professional guy to create a character for you, right? Okay, so that's what the general adversary networks, or GAN, wants to do, right? Suppose I do not know the cumulative density of the target distribution, and in practice, this is often true. Right? If I want to generate an image of a dog, right? I can collect maybe 10,000 dog images, right? It's fairly easy, but I can never be able to write down what's the underlying distribution of those pixels, right? It could be mixture Gaussian, it could be student T, it could be neither of them. Right? I don't know. Right? I only have a set of examples from the target distribution. Can I learn such a mapping T so that after applying my mapping T over some uniform random variable or whatever other standard random variable like Gaussian, standard Gaussian, so that the transform random variable will follow or respect the target distribution. This is what GAN aims for. So first, any question regarding the problem setting? I'm going to use the concrete example to emphasize this again. Like suppose I want to generate an image of new cat, right? I can collect a bunch of cat images. They're all QT, right? But I don't want to duplicate any of them, right? I want to create a brand new cat image, right? That means I want to, that means I know the underlying, there must be some hidden distribution of the cat images, right? I want to use this distribution to generate a new image of cat. Unfortunately, because I'm not able to write down the form of this distribution, the depth of this distribution is too hard. So I want to learn it. So I want to learn a mapping such that given any uniform random variable, say from uniform distribution or standard Gaussian white noise, after my learned mapping, say a neural network, I can convert it into an instance of cat. So let's see how GANs are trying to address this problem. Right? So first, we'll use a neural network to represent the mapping T we just mentioned. Right? Then the learning is to identify the parameters of the mapping network T. Right? So you can imagine that. So this is your input, right? Your input random variable, which comes from the typical uniform distribution, or can come from any other convenient distribution like standard Gaussian noise, right? So we hope that we can learn a neural network such that after transformation, your transform instances will follow some target distribution, say a Gaussian here. So the key idea, and again, it's called adversarial training. So what is adversarial training? Actually, it not only learns one network, it learns two networks. One is a generative network or faker. So that is the network we just mentioned is in charge of generating or transform some uniform random variable. Like, at the same time, we're going to learn another network, which we call discriminative network or police network. So the faker network tries to, given some random noise, uniform random variable, generate examples of very similar or resembling to the samples from the target distribution. And the police network try to differentiate the samples produced by the generative network or faker network, and the samples come from the true distribution. So you can see the difference, right? So one guy's, the faker network tries to fake things better and better, and the police network try to find out or kick out those fake images as good as possible. Right? So we want to train an excellent faker network through growing it by a stronger and stronger police network. Right? That's the key idea of the adversarial training. So then the question is, how do we fulfill or implement such adversarial training? So the procedure is like this. Right? So first, we're going to collect a bunch of examples, right? These examples are viewed as examples from the true distribution. Like from, for example, we can collect a bunch of cat images, right? They're truly cat images, right? And we know that those images are from the ground truth cat distribution, right? And then you can imagine like we got a generator of faker network, right? At the beginning, you random sample some random uniform random variable, right? and you feed it to our figure network, it generates some output, right? This output is then fed into our police network. And the police network immediately tells you that, okay, this is a fake cat image. I'm not gonna accept it. And tells the figure network. Okay. Then the figure network, according to the signal from the police network, adjusts its parameters. Right? Try to improve its technology of faking cat images. So in the next round, when we give the faker network another random noise, right? It tries to generate a better cat image, and then send to our police network. Okay? And police network say, "Oh no, again, you're doing better, but still a fake image. I can see that." So this signal or this feedback is going to the figure network. Again, the figure network accordingly adjust its weights again and try to make it better. So you can see there's a back and forth procedure, right? At the same time, because every time like police network not only see the true examples from the target distribution, but also see the fake examples. They are training and improve itself as well. So you can see that both figure network and police network are boosting themselves. And until we reach a balance such that the police network is very strong. However, the cat images faked by the figure network still cannot be differentiated by the police network. Then we're done. We reach the good point of the training. So any question regarding this procedure? Okay, and then one thing I want to mention that the faker distribution, right? So this uniform random variable is not necessary to be truly from the uniform distribution. It can come from any easy distribution, uniform Gaussian white noise, and also it's not necessary to have the same dimension of the output. So, for example, you want to generate image. This is usually very high dimensional, right? But your dimension of your random noise can be low dimensional. It's totally fine, right? And the choice is total up to the user and also the applications. Okay. So the output of the police network is not only just 0 or 1. As we mentioned, it's a discriminant network, right? It is a classifier, but it's a probabilistic classifier in that the output, the input to this police network is any example, right? It can be generated from the faker, it can be sampled from the true distribution, from our target distribution. And then the output of the police network is a probability score, meaning that the confidence the police network think the input really comes from the target distribution. So you can imagine that, okay, if this guy is 0.95, well, that means police network think the input X is very much likely coming from a target distribution, right? If there's 0.1, that means, okay, the police network think is highly unlikely this X comes from the target posterior, target distribution. Does it make sense? Okay, so now, given the definition of these two networks, right? For the figure network, the input is some random noise. The output is some data point, which can be viewed as same dimensional which has the same dimension as the example generated from the target distribution, right? And for the police network, the input is any. It can be from the Vickers network's output, right? Fake the images or the examples from sample from the target distribution, right? And then we define our training objective as follows, right? This is a minimax optimization problem, right? So we can see that we're going to maximize this objective with respect to the parameters of the police network, and minimize this objective with respect to the parameters of the Vickers network. We'll explain why. Okay. So let us first look at the form of this objective, learning objective. Right? So first, this term, right? This term, we can see that this has nothing to do with the police network. This is just this is nothing to do with the Vickers network. It's just about the police network. So you can see that the outer expectation is the examples sampled from the empirical distribution from the training data. So it basically means, okay, I'm just randomly pick up samples from the training data. And remember, every example in the training data are generated from the target distribution. Right? And then inside is logarithm of the output of the police network. So remember, the output of police network is a probability score of this network. Think X is the true sample of the target posterior, right? So remember, we want to maximize the objective with respect to police network's parameters. That means we want to maximize this probability. That's reasonable because every training example is the true example from the target distribution. So of course, to train my police network, I want to maximize my probability score over those true examples. Does it make sense? Any question about this term? I want at least for my training examples, which are true examples of the target distribution, my probability score produced by the police network should be close to 1, right? Like 0.99, 0.95, something like that. I want to at least adjust my police network to achieve that. Right? And then let us look at the second term. So what does the second term mean? So first, we are taking an expectation under the distribution of the random noise. Okay. So it means that, okay, I'm gonna take arbitrary random noise from the say uniform distribution, Gaussian white noise, whatever. And then we're gonna first feed my random noise into the current Vickers network, right? And then feed output of Vickers network to the police network. So remember, the output of the police network is just to tell that what is the probability the fake image is true, right? Right? So now I subtract 1 by this guy, take a logarithm, and maximize it. What does it mean? Maximize with respect to the W2, the police network parameters. What does it imply? What do we hope by maximizing this term with respect to W2? David. Yes, exactly, right? So you can see the discriminability here, right? So if I can make the second term as large as possible. That basically means, okay, the things inside this log, inside this expectation is as large as possible, right? That means this guy, 1 minus this guy, the output of the police network to be as small as possible, right? So remember, the output of police network is just telling the probabilistic score that the police network thing, whether the input is true, right? Come from the is true from the come from the target distribution. So since here the input to the police network are the fake images, right? So I want to train my police network such that for the fake images, my probability score to be as small as possible. That's we maximize the second term means to, right? Because when we maximize this guy, we're essentially minimizing this guy, right? We maximize this guy because we got a negative sign in front of it. So that means we're going to minimize this guy. That means we're going to minimize my prediction, minimize the probability predicted by the police network. And this probability just is the confidence of probability score that the police network think the input comes from the true posterior, comes from the target distribution. I want this score for the fake images to be as small as possible. That's the idea. So you can see if you combine the two terms together and just look at maximizing it with respect to the police network. The first term wants to increase your score of the police network for those true samples, right? True cat images, right? And second term wants you to minimize the score of the police network for those fake samples or images, cat images. So that's very simple. I want to try my best to differentiate true examples from target distribution from the fake examples from the Vickers network. Does it make sense? Okay. Any questions so far? This one? This one? Okay.
Yeah. So if you're just how do you know when the police network is bad rather than generated good?
Yeah, that's a good question. That relates to when you arrive at this training balance or stationary point. I can't give you the answer because there's no guarantee for that. But according to the gaming theory, if you really reach the point, the stationary point where you reach some kind of like such kind of point, you kind of like guarantee, okay, your police network is good enough, your Ficker network is also good enough, but it's hard to say, okay, which one is better, or not which one. It mainly depends on, especially in practice, like you use stochastic minimax optimization, it's even hard to guarantee this. Yes. Yes. That's all the problems of the training, practice training of the preliminary games. That's why later some kind of variance of the raw system game becomes even more complicated. Any other question? Yeah, right now we just focus on how we understand this formulation of this objective. Right? If you think its objective is reasonable, that's enough. Okay, so that's this view from the police network, right? I try to maximize my prediction score for this true examples. coming from the distribution, and then that's from the fixed samples, right? And then if we take another side, right? If you take the viewpoint of the Vickers network, what will happen? So first, for this part, because this has nothing to do with the Vickers network, so it can be viewed as constant, right? And then and how does the minimization influence the second term? What does this mean? So if we minimize this guy, right? If we minimize this guy, that means that I want to maximize this guy. Right? That means I want to maximize the police network's prediction score over my faked samples. Right? So I try to deceive the police network as much as possible. That's how the Vickers network get updated. Right? If the police network tell, okay, your fake image is so bad, right? My score is very low, 0.12, 0.01, right? And then I'm gonna try to minimize this whole thing, right? I try to so that I adjust the W1, right? The network parameters for Vickers, right? So that when I fake my fake image to the police network, I can increase the score. That's not enough. So you can see that this training is kind of like a battle, right? It's like battle. One side, like police network, try to maximize the differentiability between the fake images and the true images, right? And then the Vickers network tries to confound these two types of images as much as possible. So because we're doing minimax optimization, so we're searching for saddle points. You're doing minimization. The stationary point or the optimal usually stays on the saddle points, meaning that they're neither local maximum nor local minimum, right? So a saddle point is typically like this, right? Right. You got some gradient, but gradient to be 0, but it's not local minimum. It's not local maximum. So there are a variety of ways of optimizing this minimax optimization. But here we introduce the very straightforward one. Of course, as he mentioned, there's a bunch of issues in practice for this. Right? But here, for simplicity, we just introduce the idea, right? So again, at the beginning, we're going to randomly initialize the parameters for these two networks. And then we go through like many epochs or iterations, right? And then we're going to alternatingly update my police network and Vickers network. Okay. So to update the police network, you can see that you just hold W1 fixed, right? Then the problem becomes maximization problem, right? And then you just sample a mini batch of examples, sample and use the reparameterization trait and then update the police network using stochastic gradient descent. Right? And typically, you're gonna update the police network for example, k steps, and then you switch to the update of the Vickers network. And in this case, you're gonna fix W2, the Vickers network, the police network, that only minimize the objective with respect to the Vickers network. Right? Again, you're gonna use stochastic gradient descent for the update. Right? So you can see that for each iteration, we're going to do a bunch of steps of update for police network and then do steps to update the Vickers network. And then you move to the next iteration and do this alternating update again until the maximum number of iterations are done, or they reach some kind of balance So any question regarding this algorithm framework? David? Oh, this is just some hyperparameter. Like you can do in k steps of the Ficker network as well. You can choose k to be 1, or choose k to be 10. It's totally manually adjusted. This algorithm framework is just from the first paper about GAN. Their statement is that they found out they need to more systematically or more thoroughly train a police network because the differentiability of police network is very important because it can guide the improvement of the Ficker network. Okay. So this is a kind of like illustration of how GAN training evolves, right? So these black dots are the training examples, which respect some target distribution, right? And this blue curve are the distribution of the fake images, or fake samples from your Ficker network, right? So they are coming from the mapping from some uniform random noise, right? And through some transformation. So if you look at their distribution of transform points, we form this density curve, green density curve, right? And this one, the blue curve, is the probability score generated by the police network. So you can see at the beginning, both the Ficker network and the police network are not very good, right? So, of course, the faked images produced by the Ficker network is far from the target distribution. And also the score produced by the police network is kind of like non-smooth, right? It's oscillating here, right? And then after, for example, after some examples generated by faked by the Ficker's network, and then the police network can see then the police network receive those negative examples and combine with the true examples, right, from the target distribution, the police network get updated, right? So this get updated means that it get better. So for all examples like samples from the true posterior, we can see the probability score is pretty high. And for the examples generated by the Ficker's network, the probability score is pretty small, right? And then at the same time, according to the feedback of the police network, right, the Ficker's network tries to adjust its parameters as well. And at the direction of adjustments, it tries to generate examples to have a higher score of the police network, right? As a result, this is where the new set of iterations, there's a new set of examples faked by the fake networks. You can see that if you take a look at the distribution of the faked points, the green curve, right? You can see it's getting closer. And as a result, the scores made by the police network on those faked points, they're getting larger, right? That's that is consistent with the training procedure, right? And then they do this back and forth, and eventually, when they reach some balance point, set point, the distribution of the fixed points kind of overlap with the target distribution. And then for the police network, they always produce like score 1. Then it's done. Again, this is the ideal training case. It's just the illustration how these algorithms work. But in practice, there's a lot of issues. There could be an imbalance in the training of the police network and the Ficker's network, right? And also the stochastic batch. It's hard to diagnose the convergence. That's why after this seminal work. There are a lot of like variants trying to improve the stability and the training quality of the general adversarial networks. And right now, I believe the most popular variant is called GAN, WGAN. It's called a Wasserstein GAN, and there's no minimax optimization there. Okay, here, I just want to share some examples. So these are examples are drawn from the first GAN paper. Right? So those yellow bounding boxes are the training images. So use these training images, learn to generate new images of the same type, namely numbers. Right? So the left-hand side are all the numbers generated from their trained GAN. Right? So you can see it's pretty impressive, right? And also, this one is the general physics. So again, the yellow boxes are training physics, and then you can use your trained GAN model to generate new physics. It looks reasonable. And also generation of some other images. Sorry, the resolution is relatively low. It's not very clear. Right? Here I want to introduce another very interesting application of GAN. It's called stellar transfer. So that stellar transfer means, suppose you use your cell phone to take a picture, say of the flowers of the campus. So you want to throw them into a model. You don't want to change the content of the picture, but you want to change the style to be like Picasso style, like to be some kind of postmodern style paint. Right? So, so you can see that this is an image about castle in the river, and after some kind of style transfer, it gives a very cool variant of this image. Right? So how does this done? Right? So, so basically, you got a collection of Picasso's artworks as your training data, and then you can your noise will be sampled from any ordinary distribution of the images. Right? It's just to try to learn how to map your ordinary image after such kind of mapping or transmission. It kind of respects the distribution of Picasso's styles. And that's it. That's a very interesting application. And in addition, there are a lot of like funny videos in the YouTube or internet, like faking some political leaders' speech. If you're if you're interested, take a look at that. It's funny that many of them are based upon this GAN technique. Of course, right now GAN is not the state of art. Right now, it is being replaced by a new techniques like diffusion generative model. And if you're interested, you can search a very well-known open source package. It's called Stable Diffusion, released by some German university. It's just released last year. It's very, very hot, and they can use that to generate images and given text to generate images. It's very impressive. Yeah, many fun examples online. Right? Applications like deepfake, style transfer, and composition, and so on. Okay. So now we have a finished introduction of the Bayesian neural networks. So what we expect you to know, right? What are the Bayesian neural networks? Right? How do we assign some probabilistic meaning to to the neural networks? Right? What's the key idea of the backpropagation and stochastic optimization? Right? How to conduct variational inference? What is the reparameterization trick? And you're not required to implement variational autoencoder and GANs, but we do want you to know the key idea of this base by backpropagation, the key idea of variational autoencoder, and the key idea of GANs. Right? And again, in the best case, we hope that you'll be able to implement those models with the help of TensorFlow or torch projects. Those are the popular deep neural network libraries. Okay, let's stop here today. I see you on Thursday.